Good morning, everyone. We are really happy to have you here today on this Saturday morning. And we are just one day to go into the National Science Day. And here we are on our fourth talk in the Science Fest events and the second in the Life of an Eminent Scientist talk series. Today we have amongst us Professor Rajdeep Sensarma, who will be talking about the life and works of Professor P W Anderson. Professor Rajdeep himself works in the field of theoretical condensed matter and statistical physics at the Tata Institute of Fundamental Research, TIFR, India. His main area of research is the study of properties of strongly interacting quantum many-body systems, both in and out of the thermal equilibrium. He did his PhD from the Ohio State University and went on to complete his postdoc from the Harvard University and the Condensed Matter Theory Center of the University of Maryland. We are eager to hear from about Professor Anderson from Professor Sensarma. The stage is all yours, sir.
Thank you, Ashmita, and thanks for this invite to give a talk on the life of and works of Professor Philip Warren Anderson. But maybe since we are talking about life of eminent scientists, I should probably start by congratulating Professor Deepak Dhar, who is there in IISER Pune, and who just yesterday or day before won the very prestigious Boltzmann Prize in statistical mechanics. Deepak is also one of the very, very eminent scientists, and I would say you guys are very, very lucky to have him there. I've had him as a teacher first and as a colleague later. And it's a very, so congrats. I would start by just congratulating Deepak and asking you guys to, he's an incredible person so try to get as much as you can out of him. Okay, so with that, let's get back to the topic of the talk today, which is the life and works of P W Anderson. Professor Anderson died a couple of years ago in 2020, and he was born in 1923, so he had a lifespan of about 96 years. And we will see some amazing stuff about him as we go through the talk. And the title of my talk is that he's a pioneer of condensed matter physics, and we will see in what sense and what happens as we go forward. So how do we want to view P W Anderson? So any scientist, of course, is viewed in terms of what scientific work he or she has done. And he did the pioneering work on a very, very large number of topics in condensed matter physics. You usually get people who have done, something very deep in one field and so on. He has the distinction of having almost started a few fields and having done the seminal work which led to the development of large number of things in condensed matter physics. And more than just that, and you will see these numbers will soon pop up and they're kind of eye-catching. But more than that, more than just working on a very, very large number of topics and working on doing very seminal work in each of them, he basically epitomized and brought in a new culture or a way of thinking about solid state physics. Okay, so there is what you would call a modern intellectual tradition or culture of modern condensed matter, and that is entirely his creation. And you will see at some point he was quite unabashed about it, even fought for it. I think he has established that, his way of thinking is essentially how we approach the whole subject. And in that sense, he gave an intellectual coherence to condensed matter physics. You will often hear about, when you ask anybody about what is condensed matter physics, they'll talk about a lot of things, okay? Materials, magnets, superconductors, other stuff, economy, etc., etc. Once you talk about so many diverse things, the question always becomes, okay, are these all just, all different things which you are all calling condensed matter physics? Or is there some kind of binding tradition that binds them all? Is there some kind of commonality or some universality that you can think of all of these as part of one essential subject? And that commonality, that universality, that thread of binding these very, very diverse things was started by Anderson, and he was definitely the most vocal proponent of that. Okay. And one of those ideas was what you would call more is different, and we will come back and talk about what he meant by that. It's essentially trying to say that when you put many, many things together, the properties of this system or the phenomena exhibited by this system cannot be explained if you just know the properties of one or two of these constituents. There are entirely new properties which emerge simply because you have put many, many, many of these degrees of freedom together. And this led to a rejuvenation of ideas in both philosophy of science, and it started in biology in 1980s and became a matter of philosophy of science, which was called, given the name emergent phenomena, that you put many things together, new properties emerge. And it's not like, you know, they were there when you had a few particles. You can't even talk about these properties in any meaningful way when you are talking about a system of few particles. That was the key idea that he pioneered and so on. Okay, so with this, this is what we would try to cover, and I would try to show you that his life and works had all these aspects. But as in any talk, let's start with the biography. Let's start where it started. P W Anderson was born on December 13th, 1923. And his father, Harry Anderson, was a professor of plant biology in University of Illinois, Urbana. So he came from a family of educators. You know, his, I think, maternal grandfather was a professor of mathematics. His uncle was a professor of English, and so on and so forth. And he went to this school, the picture of which is shown on the right, called the University Laboratory High School. And it was a school which was run by the University of Illinois, and he graduated from there in 1940. And the reason it's called Laboratory High School is that, you know, people who are in the education department of University of Illinois would use this as a laboratory to try out their various ideas of how to teach people and so on and so forth. Okay, so that's what the school was. And one more thing you might be interested in is that if you are looking at the year 1923, and between 1940 comes the 1930s, where, you know, there was the Great Depression in US, and there was a lot of poverty and a lot of things going on. Anderson was mostly protected from it. I mean, his father had a stable job and so on. So the Great Depression didn't quite affect him in the way it affected many other Americans in those days. So he came from a relatively, he was not financially well off, but relatively financially stable family and so on. And of course, he then went to Harvard University in 1943. And it was interesting that the people who wrote recommendation letters for him to get into Harvard was his father, who was the professor of plant biology, the chair of the physics department at University of Illinois, and the chair of the classics department of the University of Illinois. And so he got to Harvard with a full scholarship. I mean, they didn't have the money to pay for Harvard education, but Anderson got into Harvard with a full scholarship. And if you again look at the timeline between 1940 and 1943, there was one more big, great event that was happening. And that was America's entry into the Second World War after the Pearl Harbor incident around 1941. And so once the US went into the Second World War, there were efforts from various universities to help the war effort. Okay, so how to get technical people into this to help in the war effort. And Harvard started something called a bachelor degree in electronic physics. And although it was called electronic physics, it was mostly electromagnetism, because they were interested in getting people to work on radars, because in those days, radar was the new technology. And so Anderson also flipped and worked in got a bachelor degree in electronic physics. And in this whole thing, he mostly learned classical physics. And very interestingly, he learned no quantum mechanics during his bachelor's degree at Harvard. Okay, so the right picture is, of course, of the Harvard campus with John Harvard's statue right there. And after graduating, he did what Harvard was priming him to do. He went to join the Naval Research Lab. Okay, this is in Washington, DC. And he worked on radio-based countermeasures which were put on warships. So the Germans had discovered bombs which were guided by radio frequency. And so they were building countermeasures to jam these radio frequencies as these bombs came in. And that was what he was working on from 1943 to 45. So nowhere near a theoretical physics research and so on and so forth. So that was the early years. In 1945, as you know, the World War II ended. And after that, Anderson decided that he should go back to Harvard and he should get his PhD from Harvard. And one of the things at that point he had said, he felt Harvard had cheated him out of a proper physics education because he had no quantum mechanics. And so he went back to Harvard and got his PhD in 1949. Now, he worked with John H. Van Vleck, who in various circles is known as the father of modern magnetism. He was his PhD advisor. He was also the chair of the department. And one of his batchmates, and who was also actually doing PhD with Van Vleck, was Thomas Kuhn. And if you have not heard of Thomas Kuhn, you should look up a book called The Structure of Scientific Revolutions. Kuhn actually became a very famous philosopher of science and so on. And if you have heard the word, for example, paradigm shift, people talking about paradigm shift, that's a word which was coined by Thomas Kuhn and so on. And the point was that, you know, in that batch, Thomas Kuhn was supposed to be the superstar in that batch and so on. Anyway, the other thing to point out is this is 1945. So the most fashionable thing to study in those days was nuclear physics, because the nuclear bomb had just exploded. And, you know, nuclear physics was growing by leaps and bounds. And Harvard had one of the most preeminent persons in those days, Julian Schwinger. But Anderson decided not to work with Schwinger. And one of the reasons he said was there were 11 students working with Schwinger and he didn't want to be the 12th. Okay, so what did he work with Van Vleck on? So the other thing that the Second World War did was it gave tremendous fillip to technology. Because of radar and this radar-related research, microwaves had become very, very much available. People knew how to control them. And as a result, there was this burst of activity where people were measuring, you know, molecules and various things. They were shining microwave and looking at transitions in molecules, atoms, etc., etc. Okay, microwaves mostly for molecules. Okay, and so Van Vleck gave Anderson the problem of trying to understand what these line shapes, these are microwave absorption lines as a function of wave numbers here of the microwave frequency. This, I believe, is for ammonia, the one that I'm showing. And so this is the title of his thesis, Theory of Pressure Broadening. So where these peaks will be was known from various quantum mechanical calculation. What was not known was how broad the peaks will be, what is called the line shape. Okay, you knew where the peak will be, you didn't know how far the signal will extend around that. And this was essentially, this broadening was because, you know, you were looking at a gas of, let's say, ammonia, and there were collisions between molecules and so on. And so the absorption lines were broadened by these collisions. And Anderson's thesis was to use quantum mechanical theory and to find all these line shapes. There's a famous story that he actually got this very complicated spectrum of ammonia and all the line shapes correct in his thesis. But in those days, his answers matched with almost all the lines, but there were 2 or 3 lines where his calculated width did not match the experimental data. And apparently Anderson's thesis has a line which says, I suggest experimental errors as possible explanations. And it turns out that was true. When people went back and measured it again, they actually fit right in where what he was predicting. So you can see he was very bold. And he said, you know, there are 14 lines or something like that. My theory matches 11. It would be very weird if it doesn't match the other 3. And that was his essential idea. And he said that. Okay, the other thing that happened at this stage of his life is, I think in 1947, he got married. And by 1948, he had his daughter, Suzanne. Okay, so essentially when he was graduating in 1949, he had a family he had to take care of. So where did he go? So in those days, the best place to go to also realize that during his physics PhD, he had not done any solid state physics. This was chemistry, okay, mostly chemistry. He was doing what you would in those days called a PhD in chemical physics. Okay. So then he went to Bell Labs. What was Bell Labs? This was an industrial lab founded by AT&T, who were looking at, you know, various kinds of technologies and so on. And the biggest thing in those days was that the transistor was discovered in the Bell Labs. This was William Shockley, John Bardeen, and Breton in 1947. And the transistor was changing everything at that point. Okay, so there's a story about how he got hired in Bell Labs. Apparently, when he applied, Bell Labs did not interview him. He was not in their shortlist or anything. So he was taking a job in a Washington State University, I think Pullman University or something like that, because he had to look after his family. And about a few weeks before he was supposed to leave for that, his advisor calls him and says, oh, where are you going? He says, well, I'm going to this Pullman college. And he says, is that where you want to go? And he says, no. So Van Vleck asks him, you know, where do you want to go? He says, of course, Bell Labs. Everybody wants to go to Bell Labs in those days, but they won't take me. Now, it turns out that Van Vleck was actually a consultant with the Bell Labs, and he simply called up William Shockley and said, you know, this is a great guy, you should hire him. So he was explicitly hired by William Shockley. And Shockley was in those days working on what are called ferroelectrics, things where, you know, you can change the polarization of the material by electric fields. And they were supposed to be interesting, next generation interesting material in those days for Bell Labs and their technology and so on. So Shockley hired Anderson with the reference from Van Vleck saying, okay, come and work with me. It turns out that he soon fell out with Shockley. Okay, many people fell out with Shockley. He was not an easy person to go around. And you just look at this line. I'll talk about it later, echoes of ab initio versus models, because what Shockley was asking him was to look at some very complicated material and write down and solve the Schrodinger equation for all the electrons in it. Okay, that was his approach. And Anderson thought that, you know, neither they had the computing power nor technology, nor was it any meaningful way of trying to do the problem. So he kind of fell out with William Shockley to the extent that it's known that Shockley wanted to fire him after 1 year. But he survived. And there were 2 people in this Bell Labs initial days who were very crucial. to his mentoring and understanding and so on. One was Charles Kittel, and this name might be familiar to you from the solid state physics book he wrote. And but Kittel was a very famous solid state physicist in those days, and then after a while he left for Berkeley. And then Gregory Vanier, whose name is associated with something called Vanier wave functions, and he had done again a lot of other things. And he also learned a lot of solid state from Elizabeth Wood, who would later go on to play a very important role in development of lasers and so on. So they were mentors, and this is the period where he now starts to learn about solid state physics, because his PhD, his naval research work had nothing to do with the solid state physics. Okay. And he stayed in Bell Labs, if you look at the top, from 1949 to 1985 when he retired. Okay. Other important milestones in his career, then in 1951 to 52, he got an invitation to visit Japan as a Fulbright scholar, and this started collaboration with Ryogo Kubo, and who is known for, if you have ever heard of Kubo formulae, the Kubo of Kubo formulae. Then in between, he took a stint at Cambridge University in England in 1961-62 at the invitation of Neville Mott. And this, just keep this in mind, this was one of the very, 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 very productive parts of his career. And we will see that many of the important things he did was associated with this period of 1961-62. And after this, then Cambridge offered him a professorship. And he said, I don't want to leave Bell Labs. So he was a half-time professor of theoretical physics in Cambridge up to 1975. At that point, he wanted to return to the United States. He got an offer at Princeton University. I think from 75 to, I think, 84, he was a half-time professor, then became a full-time professor, emeritus professor, and he stayed at Princeton University till his death. That's his career graph. He won many prizes, Oliver E. Buckley Prize in Condensed Matter in 64. The Nobel Prize came in 1977. He was a member of Royal Society, he got the National Science Medal. You know, the prizes and this does not really do justice to the man, as we will soon start to. So we will stop at the formal biography and now start to get into his scientific contributions. So any questions at this point? No?
The questions can be put in the chat box by typing, or anyone who wants to ask a question can raise your hand and ask the question.
Yeah, okay. Okay, so you can then type it. If you were thinking about it, you can type it into the chat and we'll take a look at it. Okay, Anderson was a prolific author. He wrote about 500 journal articles, technical articles. He wrote about 7 books, and these are the titles. You can see the first was on a very technical matter, Notes on Theory of Magnetism. The second two were, the second and the third is trying to basically almost redefine what is condensed matter, what are the concepts that are important in studying solids and so on. The fourth one is essentially, this is actually a very interesting book. It's basically a collection of his best papers, which is annotated by him about what they were about, what was the history behind those particular works and so on. So career in theoretical physics. The fifth one is a theory of superconductivity in high-Tc cuprates, which he wrote and later disowned. He kind of said that, well, you know, some of the things I said in that book are wrong. So he was, you know, bold and honest enough to be able to say that. Economy as an evolving complex system is this work with Kenneth Arrow, who is again a Nobel laureate in economics, about trying to use physics ideas to study economy. And then the last one was more on different notes from a thoughtful Karmagyan. And this had various different kinds of his writings, which were not explicitly technical scientific writing, but more about science policy, how science should be done, what are the interesting things, and so on and so forth. Okay, he wrote a large number of letters to editors, newspaper articles. So he was a proper public intellectual in that sense. Okay. He was a versatile scientist. And it's in fact, when Sunil wanted me to give this talk, this was what I said, it would be very hard to figure out what to put and what not to put. Okay. So what I have done is I have given you a list of things, and don't even try to read, etc. There are about 19 or 20 things here, in each of which he did some foundational or seminal or things which, you know, has been used by many people, and things which changed the kind of way the field was looked at. And that's like 20 different things that he walked on, and so on and so forth. So it's very versatile, very varied. He didn't just think about one problem essentially. And out of these, I will basically take these these three are kind of related. The localization stuff is, these are the two things I will mainly focus on. I'll talk maybe a little bit about resonating valence bonds in some ways. Okay, so that's the idea. Now, to see that what I'm saying is true, that he was not just a versatile scientist who just, you know, dabbled in everything and didn't do much. You can look at the number of things that bear his name. If you have things that have your name and they go on to, let's say, advanced textbooks, then you have done something in the field. And I have listed here, I got, I think, about 10 or 11 things off the top of my head. Worked on antiferromagnetism. He had seminal works on symmetry breaking. He had seminal works on the Higgs mechanism, which later became very important. He did it in the context of superconductivity, became very important in the context of particle physics. And that's how mostly the current theories of particle physics allows the particles to have mass. He did these two works, which was Anderson localization, which kind of changed the way we think about how current is carried or how things are carried in, let's say, alloys or, you know, disordered objects and so on, amorphous objects. And he also worked on what happens to magnetic moments. If I just put a magnetic impurity in a metal, does its magnetic moment survive, or does the electron kind of, you know, screen all the magnetic moment and you are not left with anything? And it's these two works that got him his Nobel Prize in 1977. I will not talk about, you know, things like super exchange, things like Anderson's theorem for dirty superconductors. There's a whole bunch of things here that I will not talk of. And that tells you the influence of the person, where, you know, about 10, 12 things in textbooks essentially have your name tied to it, that he was this person who actually went and did all of this. Okay, so let's start with the scientific contributions. The first one I want to talk to you about was done around when he, very early in his Bell Lab career. You can see the date, it's about 1952. And it says an approximate quantum theory of the antiferromagnetic ground state. So what's the problem? If you have spins and they are interacting, well, these are quantum spins, but you can for now just think of them as vectors or something. And they're interacting with some Hamiltonian, which looks like SI dot Sj. This is the energy function. J is positive. Then, you know, if all the spins which are close by are interacting with this, the lowest energy state will be when they're pointing in opposite direction, because that will make this SI dot Sj negative. So in some ways, if you want to think about the ground state or the low and lowest energy state, the lowest energy state will be essentially up, down, up, down, up, down, up, down. Now, this, of course, is a very interesting state, because if I take a vector SI dot Sj and I rotate all the spins by the same amount, Okay, I'm not rotating each spin by a different amount. I'm rotating all the spins by the same angle. You can convince yourself that the relative angle between the spins do not change. If I change two vectors, I take two vectors and rotate them by exactly the same amount, then the angle between them does not change. And so this is something that keeps the Hamiltonian or the energy function invariant. It doesn't change this. However, if I look at this ground state and I rotate the spins, it will look different. The spins will again be pointing in opposite direction, but they'll be pointing in some particular other direction. And this is what is called a symmetry broken phase. So there is some invariance of the energy function, and but the ground state is not invariant if you do the same kind of rotations here. And these were seen in those days. This was prompted by the fact that the other thing that happened out of the World War was that you had a nuclear bomb, so you had this neutron sources which were now coming up, and people were doing neutron scattering. They were basically shining neutron beams on materials and looking at how they scatter, and that's what was giving rise to this kind of experiments, which were actually seeing this up down up down up down up down feature of the ground state. So the first part of this paper talks about what is called a spin wave. Okay, so what is a spin wave? Well, one of the ways to see is this is an excitation where this perfect pattern is getting a bit destroyed, and sorry. So if you look at the spins, what is happening is that, okay, they are pointing almost in opposite direction, but not quite in the transverse direction. They are slightly off. You can see that this spin is not exactly opposite to that. That spin is not exactly opposite to this. And you can kind of see that if you look at the direction, that direction is basically changing with space. Okay, of course, there is just the going opposite one after another. One is in some direction, two is in the opposite direction, but not quite in the opposite direction. Now, if you look at the deviation from this, these deviations are changing in space, and these kind of excitations, this would cost you some energy, and these were called spin waves. So the first part of the paper essentially talks how to do a quantum mechanics of these spin waves. That was, however, known before in some other ways. Anderson was doing it in his own way. But the most important part was this. Okay, so here's what he asked. He said that, look, I have a theorem in quantum mechanics which tells me that if I have a ground state of any finite number of spins, let's say, or a finite number of particles, the ground state will have all the invariances of my Hamiltonian. Okay, and so if I actually take n spins, finite number of spins, and try to do a theory, the state must look like this. Is the first state that I showed you. Can you see my pointer?
Yes, sir, we can.
Yeah, okay. So this was the first state I showed you, up, down, up, down. This second thing is what will happen if I rotate all the spins by a little bit, okay? And I can rotate it by a different amount, and I will get the third thing. And then I will have, this should be added. I should basically start making superposition of all these states, which are essentially the first state, but then rotated by different angles. Okay, and he said that's what should be the ground state that we know. However, experiments seem to see, let's say, just the first one. How can this be possible? This is the second part of the paper, which was the most important part. And so he asked the following questions. Okay, this is the ground state, which has, these up down spins, but pointing in various directions. Experiments see only one of them. So one way you can think of this is that, you have a plane wave state, for example. Think of, if you know a little bit of quantum mechanics, and you will see that your free particle is a plane wave state. Whereas when you think classically of some localized particles, you start making what are called wave packets. You just superpose these kind of ground states and try to make up something that looks like just up, down, up, down, up, down. And this corresponds to a rotation like this. This is different from what I said before, because all this, there's nothing which is changing spatially. Spatially, they're always, exactly opposite to each other, but that direction itself is changing in time. And he said, okay, these should be excitations. What is the energy of these excitations? And he found that there are n such states if you have n spins, and each has energy 1 over n. And so he said if n becomes very, very large, and he estimated for a typical magnet what it would be, he said that this frequency is about 3 years, or time, so not frequency, this time is about 3 years. So no wonder the experiment was seeing only this, because to go from here to and explore all of these, it would take you about 3 years. And this started this microscopic way of understanding what we call broken symmetry. You will often hear in your course people saying that, oh, we have to take n tends to infinity to see a broken symmetry phase. This is what it means, that actually when I take n very, very large, the time it takes to actually see the full symmetry of the problem becomes very, very large. And for all practical purposes, experiments would see a broken symmetry state. This idea of symmetry breaking was then taken into high energy physics. This is what is now in general called a Goldstone mode, if you wish. But that work was done in 1960 and 62 by Nambu and Goldstone. So he was kind of ahead of his time. This resulted in Nobel Prize for Yoichiro Nambu and others in 2008 for the application of these some of these ideas to high energy physics. But he was doing it in 1952. So he was kind of quite ahead of his time. And this ideas of broken symmetry has played a big role in all his theoretical understandings as he has gone on. Okay. The next thing in the same vein is about superconductors. So what are superconductors? In 1911, Kamerlingh-Onnes found that there are some metals, if you cool them down, in this case, mercury, below 4.2 Kelvin, the resistance of the metal just vanishes. It just goes to 0. And then in 1933, Meissner and Oxenfeld found that this is a perfect these material here in the lower temperature regime is also a perfect diamagnet, which means if you try to push a magnetic field, the field lines do not enter the superconductor, they bend around the superconductor, and that's what a perfect diamagnet does. Okay, so these were the two things. Look at the timelines, 1911 and 1933. So immediately this became a problem. People wanted to understand why is something superconducting? And although there were a lot of work, the final theory had to wait till 1957 when Bardeen, Cooper, and Schrieffer, in this very, very famous paper called The Theory of Superconductivity, they basically gave a microscopic explanation for what is happening. And they said, well, what is happening is that the two electrons are binding to form what is called a Cooper pair. It's like forming a molecule, like, not exactly. And these Cooper pairs have no net momentum because I'm always binding electrons with momentum k and minus k, so that the total momentum of this pair or the molecule is 0. And if you have a boson, this Cooper pair is like a boson because electrons are fermions, 2 fermions make a boson, and then you will basically see that the basic idea was that you get a Bose-Einstein condensate of this Cooper pairs. Point of, you may not understand many of these words, but I hope you understand at some point. You may not understand at this point, but that's okay. What was important was that if you look at the introduction, they say that a main facts, a theory of superconductivity must explain are 1, 2, 3, 4, 5, and we have a theory which explains 1, 2, 3, 4, 5. Okay, so it's very, very and so everybody kind of knew that this was the correct theory. It just got so many things right that it's very hard for a theory to be wrong and get that many things right about. except it had a problem. When they tried to explain the Meissner effect, this perfect diamagnetism out of this BCS theory, one of the steps they had to take was to say the electric current is proportional to, I don't know how many of you know about A, if you have done any amount of electrodynamics, okay? You know that this is called a vector potential. Curl of this vector potential is related to the magnetic field and so on and so forth. They said that there's this kind of an equation that the current is proportional to the vector potential. Normally, in your conductor, current is proportional to the this current density is proportional to the electric field, okay? Because that's what gives you conduction. However, if you want infinite conductivity, J is proportional to A. This had many people going red guns after them because A in electrodynamics is something which is not gauge invariant. What do I mean by gauge invariant? If you write electrodynamics, not in terms of electric and magnetic fields, but in terms of vector potentials, then there is a choice that you can make. You can add to A certain things, okay? And there is some freedom for what you can add, the certain kinds of functions, okay? And that's not supposed to change any observable things in nature, because the theory has this idea that it gives you this flexibility that you can choose anything to add. Not anything, but at least a certain class of functions you can add to A and call that object as A. And electrodynamics should not change. However, on the left-hand side, you have something which is measurable, the current. Okay, so if I make A go to A prime, what happens to the current? And so this is what people meant, that you are writing it proportional to something, and that's something I should be able to change by a lot without changing any physics. That's what Maxwell tells me. But in this case, this is not going to happen. Again, this was a big blow against BCS theory, although people kind of had the idea that there's something correct in this, but it was violating something fundamental. This gets solved if you add Cooper pairs with finite momentum into the mix, and these are okay. And Anderson was one of the first to show this. I'll not go into the details of what this random phase approximation means, but there were others who were also showing it: Boglyabov, Tolmakov, and Sirkov in 1958. And again, Nambu got interested in superconductivity due to this gauge invariance issue and wrote a paper in 1960. But there's one part which is very, very important, and that's what I've highlighted, is saying that, just like I had those spin waves here, there is some other order parameter. I can change it in space, and that will also create some longitudinal waves. Okay, and these longitudinal waves have a velocity something. But when I'm saying I have a wave with a velocity, I'm basically saying that the energy is linear in momentum. Okay, I'm basically saying that the omega is some c times, let's say, q, that c is basically whatever it is, and so on and so forth. But then he says, this is in a neutral Fermi gas, but then he says, if you have Coulomb interaction, if you are really talking about, charged fermions, these waves are just unperturbed plasma oscillations. You might have done a little bit of plasma oscillations. These are oscillations of density which are at a finite frequency. Okay, whereas if I take waves and make the wavelength long and long and long, the energy of these waves go to 0. However, if it's plasma oscillation, it's remaining finite. You will hear often people talking about gapless and gapped modes, whether the energy is going to 0 or it's remaining finite. Okay, so this idea that if you actually have Coulomb interaction, these nice kind of modes of oscillations which were supposed to go to 0 energy if I make them very, very slowly varying. But this actually goes to some finite frequency. This is the first instance of what is known as Anderson-Higgs mechanism. Just to give you the context, in a particle physics, This finite frequency is called the mass of the particle. Okay, is at least related to the mass of the particle up to c square and so on. And so what this tells you is that you, in something which was in a neutral system, it was essentially massless in the high energy language, has become massive. And this is how you think of particles getting mass in high energy physics. So this was first done by Anderson in this language in 1958, was followed by Bogleibov and Nambu in 1960. Nambu also had this idea that Coulomb interaction gets out the collective mass. Okay. Now in 61, 62, I told you that Anderson was visiting Cambridge. And in Cambridge, he actually had tea with a lot of particle physicists. And he learns that they have this problem that, you know, they have some symmetries in their theory, but those symmetries lead to a lot of these waves which go to zero energy. But, you know, when they look at the real world, there are massive particles, and then they don't know how to generate those massive particles. So he writes what he had done in 1958 in a language which is more suited to high energy physics, and talking about the particularly specifically about the high energy physics problem. That's why you can see the word mass appearing here. So it's essentially a redoing what he had done in a more you know, language suited for the high energy physics, and talking specifically about that this can solve that mass problem. Okay, and this became known as the Anderson-Higgs mechanism. Okay, so the idea was that you started with a photon which whose energy went to zero as its momentum went to zero. You had a bunch of these modes, collective modes, like those spin waves I saw. But when you put them together, both become sort of, you know, finite frequency excitation. And Higgs took this to high energy physics, predicted the Higgs particle, this which was discovered in CERN, and there was Nobel Prize for François and Peter Higgs in 2013. Okay. So that's the Anderson-Higgs mechanism. He had that idea, and you can often see both in broken symmetry and in the Anderson-Higgs mechanism, he was kind of ahead of his time. I mean, he had done things, and then people redid all of that in more formal language and so on, and got those ideas become very, 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 very important. Now, in 61, 62, as I was telling you, he was visiting Cambridge University, and he was giving a course. And then Anderson's course was basically his ideas about how one should think about solids. Okay, and this became a book called Concepts in Solids. You can find that book if you want to read and so on. It's very different from standard solid books that you read. And student in his class was Brian Josephson, and Josephson in those days was already known. I mean, you know, he was a starting PhD student, but even in his undergraduate student, people would be calling up his hostel asking for Professor Josephson, because he was already known to be one of those prodigies and brilliant persons. And listening to Anderson and then doing, Josephson actually worked out something very, very important. And he said that if I put two superconductors, okay, then there is something called an order parameter, which is a complex number, which has some phase. And if there are two superconductors, the phase can be different, and then a current will flow, and this current will be related to the difference of the phase. A consequence of this is that if you keep these two superconductors at a DC voltage, you will actually get an AC current. This is very, very amazing fact that I can keep two things, just apply a DC voltage and get an AC current out of it. So Josephson worked out, he extensively discussed with Anderson and so on, but he worked out. And what is very interesting is how much credit, so Anderson was very, very careful not to take credit for this. And Josephson got the 1973 Nobel Prize for this work. And later his writing, I hope it was no coincidence that these developments occurred in the thoughtful and stimulating atmosphere characteristic of Cavendish, but the specific achievement was Josephson's own. This young man of 22 conceived this entire thing and carried it through to a successful conclusion. He was a very generous mentor. He made sure that, you know, Josephson got all the credit that he deserved, and that's all. Okay. So how am I doing on time? So we can go fast or slow depending on that.
It's 11:56 at this moment, so we can go on till 12:15.
Okay, fine. Should let me go a little faster, but maybe and not give you all the details. So the second thing that I want to talk to you about, okay, so Anderson is now back at Bell Labs, and there's this person called George Fair, who is actually an experimentalist, and he's trying to look at some weird object where you have a silicon and you have put some phosphorus inside it. Why was he looking at it? You know, the early transistors in semiconductors were all germanium, but in those days it was kind of understood that silicon was going to become the important material that it became later. And so Bell Labs, being technical industrial company, they were very interested in silicon, and they hired George Fair. George Fair actually was inventor of something called electron nuclear double resonance, and he's actually better known for studying structures of chlorophyll and so on. And so in biology, he is a big name and so on. What Fair's experiment showed was when you basically, take particles, this phosphorus in a particular spin state, and you just drive it to some other spin state, and you ask how slowly or fast it relaxes. The relaxation of spins were very slow, and they were orders of magnitude off from estimates from those theories. But those theories assume that the spins can diffuse, that the spins can move around, and they are not static in their fixed location. And this led Anderson to ask whether this is happening simply because the spins are not moving at all. There's absence of diffusion. Okay, normally when you have this kind of a system, you would think, oh, I'm going like this, maybe I'm coming back, I'm doing some sort of a random walk. But Anderson asked, is there an absence of diffusion? Maybe that's what will explain this experiment. So it starts from a very detailed experiment and so on. And he writes this paper, which has become an iconic paper, which just says that absence of diffusion in certain random lattices. So what's the idea? If you have a perfect lattice, perfect regularity, then if you look at the quantum mechanical wave function, the wave function looks like the top one. It is extended. It's a wave-like, so electrons can flow from one end to the other end. Whereas if you have random potentials, okay, if these are not perfect, some of it is here, some of it is there, okay, and then these variations of these potentials has a weight W, then if W is large, if it's, if the potentials are very rugged landscape, for example, this is how the wave function will look. It's called a localized wave function. You can see it's not propagating, it's decaying as I go away from some center. Okay. Two things. He's no longer talking about spins. He's just made it into a problem of electrons hopping on a lattice. And this you will see is something that was very, very radical departure from standard transport theory, which was essentially about starting with wave-like states and doing a little bit of juggling due to the potential, whereas he's starting saying that, oh no, nothing moves, and let's see if this localized wave function survives. This was the main idea of Anderson localization. It had very little immediate impact. Nobody looked at it really. For example, other than Sir Neville Mott, and you can see in 1970, Mott, in an introduction to his paper, Abstract, is saying that, neither Anderson's conclusions nor those of the present author have been universally accepted. He kind of laments. So nobody is paying attention to this very, very interesting thing. Okay. Also taken up by David Thouless, who won his own Nobel Prize for other work not related to this. What they were doing was they were relating this idea to measurable objects like conductivity, conductance, and so on and so on. So that was a big thing that they were doing. And then nothing happened actually in between with Mott and Thouless. It got enough acceptance that Anderson actually got his Nobel Prize for the localization work. Then later in 1979, And this has an Indian connection with this very famous gang of four paper, Elihu Abrahams, Anderson, Don Licciardello, and T.V. Ramakrishnan, who was initially at IIT Kanpur and then IISc for a very long time. They wrote this very, very famous paper, and then it kind of, became a very mainstream thing. People started doing all sorts of things with it. People found that this is implicatures in nature. It's not about electrons. You can do it with light. You can do it with other stuff, and it remains still a current topic of very, very active research. Okay, so this is a field that was completely opened up by Anderson. Nobody thought about it. Nobody would think in this language before that walk. Okay, so maybe I can skip the local moments part because I put it there because this is part of his Nobel Prize, but it's a more technical award. I would just like to point out one thing. If you have heard of something called renormalization group, which was discovered by Ken Wilson in 1975, for which he got his Nobel Prize, and which actually allows us to now think of, how to think about systems and so on. Anderson was doing something very, very similar, but much before Ken Wilson in 1970. So again, he was kind of ahead of his time. He was doing things which later became much more formal, much more useful, much more textbook. So Nobel Prize came in 1977. It was given to Anderson. And now you have seen these two characters already, Sir Neville Mott, and his old advisor, Van Vleck. Okay, his PhD advisor was given for their theoretical investigations of electronic structure of magnetic and disorder systems. Anderson getting his Nobel Prize, all the Nobel laureates here. Let me talk a little bit in the time that is left about I said he was also created this intellectual underpinning of what we now in modern day call condensed metaphysics. And one of the things that he did was, it used to be called solid state physics. This name was his own invention, essentially, condensed metaphysics. It was a bit of trying to rebrand the subject, but it also had its reasons for rebranding and how it kind of differed. The idea was that the Schrodinger equation was very, very successful in describing atoms, molecules, chemistry, etc., etc. And then people said, well, use the Schrodinger equation to solve for the full solid. Okay. And this, of course, meant you work with all the details of all the electronic states and all sorts of things. And the focus in those days was on finding out why one material is different from another. Okay, that was maybe this has this other orbital, maybe that is what is giving me. That's the kind of thing people were doing research. Okay, and this was getting mocked by people like, let's say, Pauli, people like even Gell-Mann, I believe. Okay, and Anderson did basically reorient this. He said that there's no point in doing all the details. Okay, he said make simple models out of this, which strip away the details, but has enough things which illustrate the underlying mechanisms of what is happening. Okay, and instead of focusing on why one material is different from another, focus on what is common, what is universal, what are these universal principles which are guiding properties of many particles. And that's the sort of, if you wish, intellectual deviations which takes you from solid state physics towards condensed metaphysics. You ask different set of questions. You ask, your kind of goal is slightly different than knowing about every different material. Okay, and here is essentially what Anderson means, and this he has actually said very well in his Nobel lecture, so I'm just quoting from that. This, of course, is the famous example of a bull drawn by Picasso, and Picasso is basically trying to show how, as you can basically go from all the details to just the structural part and how what lines you keep, what happens, and so on. It's a very famous painting by Pablo Picasso. And that's basically like, he says the art of model building is exclusion of real but irrelevant parts of the problem. And this has hazards for builder and reader. Builder may leave out something which is relevant, and the reader may be armed with too sophisticated data or too accurate a computation and say, oh, this small thing doesn't match, okay, from your model. And he says that the model said the schematic things whose main aim is to demonstrate the big ideas and the demonstration of a possibility. Don't expect this model to, be able to compute and go on giving you every small details of your data. And then he makes a very, very bold statement. He says, very often such a simplified model. By the way, I was listening to Deepak yesterday. This was, again, something Deepak was emphasizing in his talk yesterday or day before, one of those days. He says, very often, such a simplified model throws more light on real workings of nature than any number of ab initio calculations of individuals. I calculate everything, I put in everything, and I calculate one particular situation. I have another material, I again put in everything, and I calculate everything. That's not the way to do it, okay? Because that doesn't tell me what is really happening. And the last line is very, very bold if you think about it, which even where correct, he's saying even if you can do it correctly, it contains so much detail that it conceals rather than reveals reality. Okay, it's not this. We often hear, oh, statistical mechanics. Oh, are you doing it because you don't have enough computers? Right? If you had computers, would you have put in all the details and actually calculated trajectories of all the particles? And the answer is no, because you would have gotten everything, but you would not have learned anything. And he ends by saying, after all, the perfect computation simply reproduces nature. It doesn't explain it. Okay, so this is his very famous article, which he was writing somewhat in reply to particle physicists in some ways. And he says that, oh, well, there is this idea that physics is reductionist. Like, if I want to understand the dewdrop, I first understand the water. If I want to understand water, I first understand hydrogen, then I understand quarks, and so on. So I should understand only the more fundamental blocks, the smaller and smaller. This, of course, takes you to higher and higher energy. Okay, and he says that, however, even if you know how to do this, this does not mean that you know how to build it back. The main fallacy is that the reductionist hypothesis does not mean a constructionist one. Ability to reduce everything to simple fundamental laws does not imply the ability to start from those laws and reconstruct the universe. Okay, and this is something that he has essentially championed all his life, various ways. These were the things which had resonance with ideas of emergence. And then this went into this idea that, when you put many things together, they're complex systems, they're new properties. And he basically says at each level of complexity, entirely new properties appear. And this understanding these new properties is as fundamental as understanding what the constituent does, because you cannot just know what the constituent does and apply it to get this. And that's his main big intellectual underpinning. He actually went toe to toe with particle physicists. Especially in the case of superconducting supercollider. He was one of the vocal public opponents of funding this project in the US. And in a kind of clash of titans, he and Steven Weinberg actually testified to the US Senate on the same day. Weinberg supporting the project and Anderson opposing the project, saying that, it's taking up too much money for one project. There are so many other interesting things to do, and so on and so forth. The SSC was not funded, and he probably earned the enmity of a whole generation of particle physicists for the role he played in this. Okay, I'm almost towards the end, and I don't want to talk about the high TC and RVB. So I don't want to at least talk about the technical aspects of high TC and RVB. So in '86, people found a new class of superconductors. Okay. Yeah, and you remember '84 was when Anderson had resigned from Bell Labs, and he was doing this complexity and all of those stuff, etc., etc. He left all of that and he came back. He came back from retirement, okay? And in '87, he wrote a very influential paper which led to various things. But he could not, this is one place where he could not convince. He spent 20 years working on it, okay? And he could not in the end completely convince the community that what he was saying is right. This is still an open problem, of course, but he spent the next 20 years, which is between his 70s and 90s. Just think of the age, working on it and trying to convince people very hard that what he's saying is actually going to happen. I just want you to look at these last two figures. His last published paper in Physical Review Letters, I believe, is in 2011 when he was 88, or 2012 when he was 88. Okay, that's his last published. But even after that, he kept writing and putting articles on archive till he was 94 years old in 2018, and he died in 96 at 2020. It's an amazing feat where at 90, 94, you are writing articles, you're sharp enough to write articles, and you still have the energy and will to keep writing that. So I will basically just end by saying this. He was a very intuitive physicist. He was not someone who would do a lot of math to get to the problem. He would almost first guess the answer. He was someone who was very grounded to the experiments. He almost all his papers start from saying, oh, there's this experiment, this is something is seen, we need to explain this. Okay. However, he knew how to abstract out of it and get to things which became very fundamental and, created the foundations of modern condensed metaphysics. And it's also that people do it once, twice. He has done it many, many times. He's the man who revealed the workings of nature many, many times. And he was the strongest public advocate for the science of men. Okay, so I will stop here. I guess I'm a little bit over time, but there's some resources you can look at. I don't want to, and if you have questions, we can take up.
Thank you, sir. We already have a question in the chat box. Aditya Shukla asks, Anderson was friends with Thomas Kuhn, a philosopher, which motivated him towards scientific philosophy, especially towards emergence. Can you tell us more about his work on this?
On emergence? And so Anderson's work on emergence, or you're asking about Thomas Kuhn's?
I think Aditya, you can
and Anderson's. Okay. Okay, so maybe I can tell you. So what he's trying to say in many of these, okay, maybe the correct thing to do is to go here. Actually, maybe the best thing to do is to start here. Okay, so the idea of emergence is basically, he is saying that, you would often see, even sometimes you'd see these cartoons which would say, oh, chemistry is applied physics, physics is applied mathematics, X is applied Y, okay? Or psychology is applied physiology, sociology is applied psychology. These are from actually his own sort of article on more is different. And he was basically trying to say that, look, that is not the case. Okay, so the basic idea is there are properties which it's not that, okay, this because it's not a quantitative thing that something became finite when you put many particles. I mean, that may be one way of looking at it. The idea is there are properties which you cannot meaningfully talk about in a few particle system or a few degrees of freedom system. Okay, so he's basically saying, so one example where you can do this, for example, is say, you want to study the rigid body motion, you study the point particle, then you can build up the rigid body motion essentially from that point particle and knowing Newton's laws. He's saying that no, but when you put many things together, it's not always that case. You cannot always extrapolate. You have to think in a new language. Okay, and that's the word emergence, because it's not that I could have thought about it for a few particles and I think about it for many particles, it is zero here and it's finite here. It's saying that there are things that you can't think about. And the approach to this object systems with many degrees of freedom And he later talks about in his more is different about what his idea is. He's basically talking about, in fact, in those days when it had not exploded because of the quantum computation thing, he still talks about, for example, he says, look, you have to think about information, how information propagates in time and in space. And this is not something that you talk about when you are talking of, let's say, 1 particle, 2 particle, 10 particle, and so on. So he says entirely new class of language, entirely new class of approaches, things. And that's the idea of emergence, if you wish. Does that make sense to you? So one of the things he specifically talks about, of course, is symmetry breaking. Is that, symmetries are kind of fundamental to laws of very small particles and so on and so forth. But I see something where the symmetry is broken. And there is no sense in which 10 water molecules. So there's no sense I can talk about in which I can think of a solid of 10 water molecules, but I can think of ice and its properties and its various things when I have many degrees.
Okay. Thank you, sir. Sir, also I wanted to ask, in the same lines, I have recently read about reductionism in terms of physiology. So there also, when we keep on reducing systems, say from the body to the organs, to a particular organ to the cell. So when we go on reducing things, that order plays out in a right way. But from the heart, say from the heart to the rest of the body, the reverse does not, is not that straight.
It doesn't walk that straightforwardly. Yes.
So is that true for every reductionist system? Like you talked in the towards the end that he was saying that.
So yes, so if the idea, one of the things, at least in cases where the reductionism does not work, or the it works one way, but you cannot build it back up that easily, is when things are what is called interacting. So the idea is, so suppose I have small number of constituents, whatever they may be, they are doing something, I know what they are doing, there are laws that govern what they are doing. But when I put 2 of them, okay, does the presence of the other influence what this original, let's say, object, let me call it A, okay, I'm putting another object B nearby it, okay, does it change what I'm doing? And you can see this in various ways in biology, that yes, even having the fact that you have other cells, or if you, so he talks about thinking about, in that case, of functionality. He said, you have some physical structure, right? But think of functional structures and what goes on, let's say, in biology. Things are influenced by other things, being present or absent, and so on and so forth. And when you have this kind of interactions, sometimes you are lucky that what you end up getting is essentially what you would have guessed from just, one particle. An example of this in the case of physics is actually metals, where essentially if I knew what one electron does, in many cases for the metals, I would be able to figure out what the answer is. However, if I go to a magnet or a superconductor, I don't. So the claim is that there are situations where the reductionism can be reversed easily, but there are many situations where it cannot be, and they almost always involve things talking to each other and influencing each other's behavior very strongly.
Yes. Thank you, sir. Do we have any more questions? If anyone would like to raise their hand.
Sir, may I speak?
Yeah.
May I ask my question?
Yeah. Go on.
So you were talking about the symmetry breaking in antiferromagnet, and we know that in n tends to infinity limit that we have that ground state manifold, like the system can explore all the kind of different continuous rotations. But like in finite system, what exactly is stopping the system to explore all the ground state? I mean, like why can't we?
No, that's a good question. In fact, that was the question Anderson was trying to answer. So let me just go back to that. So you are right. So if I have finite n, why can't I see in my experiment? So for example, when I see my experiment, why can't I see the spins doing what the, let's say the graphic is doing, whereas I see the things. So, the graphic has been speeded up. So what he was showing was that if you have n spins, okay, the rotation time scale, time period is about 3 years. So yes, you will explore these things in a typical sample size. Okay, so now it depends on how many spins I have. Okay, and he actually gives this this is very interesting, straight from more is different. He says, let's try to build up. So the first thing he talks about is ammonia. Okay, ammonia is 4 objects, NH3, and the rules of fundamental interactions tell you that ammonia should not have a dipole moment. Okay, it cannot have a dipole moment. If you look at the structure of ammonia, I hope you kind of know. Let me see if I can draw. I probably can't draw. Is that there is a nitrogen on top and there are 3 hydrogens at the base of a pyramid, right? This must have a dipole moment because the top is not the same as the bottom, right? So there actually, if you look at this, you'll have dipole moments. But then what happens is there is another state where, the base of the pyramid, the top nitrogen is inverted. The pyramid is pointing downwards. And if you put an ammonia molecule in this top pyramid state, what it does is it does actually what any quantum mechanical state would do. It keeps oscillating between the top pyramid and the bottom pyramid. So average dipole moment will be 0. Okay. And you can look for its frequency. This is, by the way, this is one of the main frequencies that people look at in this ammonia microwave spectroscopy, which he started his career with. And this is some 10 to the power 10 hertz or something like that. Okay. Then he says, let's build up. Okay, let's make something heavier like fluorine or something, add instead of maybe look at PF3 or something, and you will see that this has become slow. Okay, by the time you get to 40 particles, something like let's say sugar that you produce. Sugar, for example, has chirality, it has handedness, right? You talk about handedness of sugars, and they are about 40 molecules long. So by that n, okay, so the time is scaling with n, and so by 40, the time is so long that any normal experiment will not, it will basically see that the sugar has a particular handedness. Okay, if you waited for longer than that, you would see that it flips between handedness, but there's those time scales by this time are maybe years or something like that. Okay, for antiferromagnet, what he said is, if you were going to wait for 3 years, the system should do this, but you don't keep a sample for 3 years and continuously observe that it is rotating. Okay, so that's the point, and in many cases this answer is age of the universe, and then you can ask, okay, yes, my system will, and I will be able to see it if I wait till the edge of the universe, but what will I do with that? And it's very interesting that you can actually build up from small to large and see this frequency become smaller and smaller, or this time period become larger and larger in the same kind of system. Does that answer your question?
Yeah.
Yeah. So if it is small enough, you can see. That's the point.
Do we have any more questions? Okay, so then I would like to ask something. Like this may be totally because of my lack of knowledge also, but I just wanted to I just wanted to ask. I don't have any physics subjects at the moment, but I had quantum physics last semester. Throughout the course, I don't know why. Whenever I'm studying something related to quantum physics or chemistry, it sometimes feels like the pattern is not in nature. Like. Uh, in nature or in the real state, it's just scattered dots, and we are trying to make a pattern out of it. So, like, how does that play, sir? Could you?
I think, well, okay, maybe I can give a little bit more concrete way of saying that is, when we ultimately, it's not a question of whether it's in nature, it's that when we measure, okay, all our measurements are mostly classical, or most of the measurements are classical, okay? So the way we perceive nature in the end is classical, okay? At least our day-to-day experience of nature is very classical, okay? For example, there is an underlying, there are many things which would not have worked in the way that you would like to do without quantum mechanics working in that particular way, okay? And that's the feeling that you are getting, that there are actually some experiments which would test that things are not classical but quantum mechanical, but they are not in your everyday experience, okay? They're not, that's something that's happening all around you, okay? So you have to really build experiments and do these to basically test that the underlying theory is quantum mechanics. However, if you take that underlying theory to be quantum mechanics, many of the other things that you observe actually makes complete sense, okay? So that's the one thing. And the second thing I would say is that if you go back and ask what is the idea of any science, okay? It is to make, or any theoretical science, let me say, is to make, to connect dots which we see in nature, to provide an underlying sort of framework which can, then connect all the dots, or as many dots as you can connect, and that becomes a more and more applicable theory, which is not restricted to a small set of things. Okay, for example, Newton's laws, per se, you can say that, okay, I mean, who told me Newton's laws should be correct? Well, we go to nature, we see something, and they seem to follow Newton's laws. Okay, that's the basis of saying that Newton's law is correct, right? At some level. Okay. In fact, if you think about it in that way, any theoretical thing is always one of the ways to picture to keep in mind is nature is giving you glimpses. Okay, it's not giving you continuously everything that it does. And it's your job then to try and build a framework which basically, as you said, connect the dots. It basically can explain all the glimpses that nature is providing. In fact, that is all of physics, if you wish.
Yeah. Thank you, sir.
Okay.
Do we have any more questions? Okay, then if we have come to the end of the question and answer session, I'd like to thank sir for this wonderful session. And we are really grateful to have you, sir. Thank you very much. I would also like to thank Professor Rajesh and Professor Sunil Mukhi for helping us arrange this session, and wish everyone a wonderful National Science Day. We'll still be having the talks throughout the weekend. So the next talk starts 6 p.m. today, and we'll be hosting Professor Sarika Jalan from IIT Indore. We'll be speaking about chaos in biological systems or in life sciences. So stay tuned, and we hope to see you again. Thank you very much, sir, and thank you everybody for joining.
Thank you, everybody. Thanks. It was very nice coming and giving a talk. Yeah.